Hi, my name is Ali Shirsavar from Biricha Digital, and in this video we're going to talk about why switching power supplies are so noisy. In particular, we're going to talk about the rate of change of current dI/dt and rate of change of voltage dV/dt. We're going to explain all of these and then show them in the lab. If you remember from our previous videos, we talked about modes of noise coupling, and in particular capacitive coupling and inductive coupling. And we showed that as the frequency went up, noise managed to couple quite well using these parasitic inductances and capacitances on our PCB. But a switch mode power supply is only switching at rates of a couple of 100 kilohertz. These modes of noise coupling were becoming very effective in orders of megahertz. So why is it that a switch mode power supply, switching for simplicity, let us say at 100 kilohertz, can be so noisy? And the reason is that we are not talking about a 100 kilohertz sine wave here. We're talking about a 100 kilohertz square wave, and of course, according to Fourier, we know that the square wave contains quite a lot of high harmonics. Let me show you by way of a drawing. Let us say that I just have a sine wave. For simplicity, let me say that is 100 kilohertz, and I'm going to draw it like so. This is my 100 kilohertz. A power supply, it is not a sine wave. It's a square wave. Now, if I take this sine wave and I add a third harmonic to it, the addition of this third harmonic to this fundamental, so if that's where 100 kilohertz, this will be 300 kilohertz, will give me a resultant whose rising edge is sharper and its top is a little bit flatter. So what it will look like, the resultant of a fundamental plus its third harmonic, would be something like this. And you'll see, if you compare the gradient of the blue fundamental to the resultant, that this has raised a bit and it becomes sharper. Now, let me add the fifth harmonic to this. Okay, it's going to get a little bit difficult to draw, so I'm gonna try my best. That's the tip. It's going to be like that. And that is, the green is now my fifth harmonic. So now if I add the fundamental plus the third, which is the red, plus the green, which is the fifth, it's going to get even sharper, it's going to get even flatter, and it's going to have a little bit more wiggle at the top. So I'm going to now draw that with the only, how many colors have I got? Oh, I've already got all the colors. Let us do it again in black. Right? So this edge is going to become sharper, this bit is going to get flatter, I'm going to get more wiggle, and it's going to do that. Okay? Now let us compare then only fundamental and third harmonic, the gradient is here, and the fifth harmonic is even sharper. If I continue adding 7th, 9th, 11th, and all the way up, more and more I add, this edge becomes sharper and sharper and sharper, and this edge becomes flatter and flatter and flatter, and of course that is Fourier in practice for you. Therefore, if I have a switch mode power supply where I am switching a square wave, I have got a very sharp edge, shows that I've got very high harmonics. Okay, now let us say, again for simplicity, I have got a switch mode power supply that is switching at a rate of 100 kilohertz. And let us say that when I turn the switch on, I'll go from 0 amps to 10 amps. Right? In a period of MOSFET rise time of, for simplicity, let us say 10 nanoseconds. So that gives me a rise time for this square wave of the current of somewhere in the region of 1 amps per nanosecond, which would be 1 gigaamps per second. And of course, this fast rise time, when decomposed into its Fourier components, will have many high harmonics, and we're going to show that in the lab. The same applies to a voltage. Let us say that at the same time that this switch turns on, the voltage across the MOSFET will fall, and that is falling now from 10 volts down to 0 volts. Again, I would have something like 1 volt per nanosecond of this, the gradient of this edge, which will have many harmonics. And of course, the higher the harmonics, when it gets into megahertz region, a star will start capacitively coupling in terms of voltage, or inductively coupling in terms of current. This is my high dI/dt, this is my high dV/dt. They will couple, and that's why even at 100 kilohertz power supply can be very noisy. So what we're going to do now is going to go to the lab and actually show you the harmonic content of a very fast rise time of a voltage waveform. Okay, so first let us look at Fourier transform of a square wave in an animation, because that really shows how, as we increase the number of harmonics, we'll have a sharper edge on our square wave, or in other words, the sharper the edge of the square wave, the more harmonic content it has. So here I have my animation. Let me show you. At the moment, I have just got my fundamental. That's one sine wave. So let us now add the third harmonic. And you can see this red line now is a third harmonic, and the black line here is the resultant of the fundamental in blue with third harmonic in red. And you can already see that this edge has sharpened and the top has flattened a little bit. So let us now add the fifth. Let's go third, fifth. And now you have got the fundamental. Red is the third and yellow is the fifth. And you can see that the resultant, the edge has got even sharper and top has got flatter, and you've got these 5 wiggles here on it. Okay, now let us add the seventh. That's my third, fifth, seventh. And you can see that it's got even sharper. And now I'm going to add the ninth. You can see now you have third, fifth, seventh, ninth, and it's going to repeat. Just look at this edge here, how it sharpens as I add the extra harmonics. So again, third, fifth, seventh, ninth, and so on. It follows, therefore, that if you have got a current that is changing very fast, in other words, it's got very high dI/dt, and this edge here is extremely sharp, it has got very high harmonic content, and of course that high frequency is what couples with the inductive parasitic inductances on the PCB. The same thing applies to a voltage waveform that has got a very sharp edge, and again that will have very high harmonic content, and that will capacitively couple just like we showed in the other videos. So another demo that I have got for you, let us look at now at the oscilloscope, whereby I now have a signal generator, and I have set this rise time to be 100 nanoseconds. And 100 nanoseconds is quite slow, and down here the instrument is doing the Fourier transform of it, and you can see the harmonic content. This is 10 megahertz here, is going up to around 100 megahertz, and you can see that beyond a few tens of megahertz, actually the amount of harmonic content is in lower and lower and lower, and the noise gets less and less and less. Now what I'm going to do is I'm going to sharpen this edge, and as I sharpen this edge, just have a look at the harmonic content and how the amplitude of the higher frequencies increases. So I'm on 100 nanoseconds at the moment. Let us go, let's say, to 80. You can immediately see that the amplitude of the harmonics here increases. Now let us go perhaps to 50. You can immediately again see it's got even bigger. Now keep your eye on this point here as I go from 50 to maybe 20. You can see how much more noisy it got, and you can see that this is now a lot sharper than it used to be, and of course it has got higher harmonic content. Let us now make it very fast. I think I can take this down to around 5 nanoseconds. There we go. Look at that. This is now a very sharp edge of 5 nanoseconds is taking for it to move from -5 volts to +5 volts. And of course, there's all these spikes all the way up to 100 megahertz, and it is these high frequency components that will couple with capacitances and inductances, and that is why your power supply, even though it might be switching at only 100 kilohertz, if the rise time is fast enough, dI/dt, dV/dt is large enough, the noise will couple with other parts of the circuit. So thank you for watching the video. We run power supply design workshops and EMC workshops regularly in both North America and Europe. So please come and join us, and thank you for watching.